we see this viscosity? For the liquid only. If a liquid is in motion, the adjacent layers will exert force on each other to oppose relative motion between the layers. That is called like this particular property is called as a viscosity. Fine. So what will happen to pressure? See, I can vary the pressure. So if I increase or decrease the pressure, any effect on the viscosity? No, the viscosity will not change. So tell me like what is viscosity? This particular symbol. This is what no. So anything will happen to this quotient of viscosity or all this particular property that one. So it will not change. It is insensitive to pressure. So for almost all the liquids, water is an exception is telling. Its viscosity decreases with increasing in pressure at constant temperature. There's just information at our level. I think this information will be sufficient and very important. It is also stressed in inside the book. Almost all the liquids, if you vary pressure, viscosity will not change. The eta will not change. For water or pen, increase pressure, viscosity decreases. I'll slightly underline it. Are you seeing this? But for the viscosity usually rises with pressure at the viscosity of liquid usually rises with pressure at constant temperature. Water is then rises with pressure at constant temperature. Only at higher pressures, that one. I think you should be very careful about relatively insensitive is telling until high pressure. When high pressure is maintained, the liquid, the viscosity of liquid what will happen as you increase pressure, the viscosity also will increases. Water is an exception where as you increase pressure, the viscosity decreases. For low pressures, there won't be any change in viscosity. I think you should able to grasp this idea. Only at high pressures we can notice there'll be increase in viscosity as we increase pressure. These are information. Water what will happen as we increase pressure, viscosity decreases. At low pressure, no change in viscosity. Fine. For most of cases, practical instruct, however, the effect of pressure on viscosity of liquids can be ignored. This was the condition they have put it. Okay, what happens to temperature? As you increase temperature, the viscosity decreases. Any reason for that? As you increase temperature, the vibration of molecules will increase. Due to vibrations, what will happen? The interaction between the molecules will decrease and the viscous drag will decrease. And there's a reason what we can give. As you increase the temperature, because what is the viscosity? It's a due to interaction of molecules of the adjacent layers. So as you rise the temperature, the interaction between molecules decreases and that will decrease the viscosity. This is the one primary reason what we can give. Fine. Okay, next afterward, this is something streamline flow and turbulent flow is telling. Okay, I can't separate. Okay, now I'll highlight. For streamline flow in narrow pipes, what actually won't once again I'm going for this. So what is the basic support for this particular thing? So you what is the formula? So I should take help of this formula. We know critical velocity is equal to eta Reynolds number by rho into this diameter of inner diameter of pipe. Will I agree this? If velocity of the flow less than critical streamline flow. If velocity of fluid greater than critical velocity, streamline or laminar it is, then it is turbulent flow. Okay, no, let's analyze one thing. For a streamline to flow, for a streamline flow in narrow pipes means what is the diameter will be very small. Okay, like this, high viscosity, low density. Then critical velocity, what happen will be more. Yes, I'll get a streamline flow. Then broader pipes, definitely radius will be large. Then critical velocity will be very less because so for that particular what happened, the viscosity should be low, viscosity will be less, and the density will be high. Broader pipes, what happened, the liquid should move with a less velocity. There's a main reason. So why you are thinking like this here? For broader pipes, what when the liquid should flow with a less speed, then only what when streamline will occur. For critical velocity to be less, these are the conditions should be satisfied. Narrow pipe, the liquid can flow with high speed. For broader pipe, the liquid should flow with a lower speed. Then only streamline will occur. So for the lower speed, definitely what is the condition required? This is a requirement. Is it okay? This is the simplest thing. All these are theoretical ideas. I'm just wanted to put it one place. Now regarding Stokes law, we'll go for Stokes law again. Any condition for Stokes law means it is valid for all the in any situation, or so any constraints will put it. So Stokes law. Stokes law is applicable. First thing, sphere should be rigid. Next again, liquid around the sphere must be laminar. No, 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 no. Don't neglect radius. Huh? Don't do all that one. How you neglect radius? It should not be that one. Just accept the data. Okay, this is one basic liquid around the sphere must be laminar flow. Next again, what should be the liquid boundary of the liquid? Infinite boundary of liquid. Boundary of liquid must be infinite. Okay, these are a very primary conditions for the Stokes law to be valid. So possibility of anyway theoretical things they'll ask you. This is something it's a data. Just we should have some information because as a student, I think in exam not possible. There's a theoretical information which if a students remembers, it'll be much easier. Stokes law is something very important. We should strict condition for if there's some elastic body, if you release, no, Stokes law is not applicable. The reason for that, because the sphere as it moves now due to viscous drag, it may change shape like this. Then what will happen? Even the buoyant force formula also will change. Even the viscous drag formula also will change, no? From spherical to this one. So therefore, it's telling that to be rigid. Sphere must be rigid here. Because see, the 6 pi eta RV, you brought it to be spherical. But if the sphere as it moves, if it is elastic, it can undergo deformation. If it takes like this, no longer that formula is applicable. No, therefore, the law is applicable only when there's a condition. And the liquid around the sphere must be laminar flow. Okay, these are the some elementary things which we are supposed to remember things. So when it comes in exam, no, so these are some theoretical things which books they have stressed it. Okay, let's take some few simple questions. Now, if we have a